All right, good afternoon, everybody. Today we're going to talk about section 4.1, maxima and minima. And that's a singular maximum value and a singular minimum value versus maxima, which is multiple maximum values, and minima, which is multiple minimum values. So let's talk about the idea of an absolute maximum. We're going to let our function f be defined on a set D that contains the point C. Now, D can be an interval, D can be a collection of intervals. It's just important that we have this range of values and that C is in it. If f evaluated at C is greater than f evaluated at x, where x is in our domain, then f of C is an absolute maximum value of f on D. And what does this look like? This looks like the graph here. We have 4 minus x squared on the interval negative infinity to positive infinity. We see that when x equals 0, y equals 4, which is the maximum value of our function right there. And on the graph, we see that it's a maximum value too. So if we have an absolute maximum, we better have an absolute minimum. Let f be defined as a before, it's a function on a set D containing a point C. If f evaluated at our point C is always less than f evaluated at x for all values of x in D, then f of C is an absolute minimum value of f on D. And this looks like the graph y equals x squared minus 4. We've got a minimum value when x equals 0, y equals negative 4. And you can see graphically that we have a minimum value here as well. Our interval is negative infinity to positive infinity, but it doesn't always have to be the entire domain. It could be from 0 to 2, it could be from 0 to 1, and then we would have different values for our minimum. So an absolute extreme value is either an absolute maximum or an absolute minimum. So if I ask you to find the extreme value, the absolute extreme values, I need you to find both the absolute maximum and the absolute minimum. I want both of those. And this brings us to the extreme value theorem. A function that is continuous on a closed interval, that is including a and including b, has an absolute maximum and an absolute minimum value on that interval. Now, it's important the way that this is worded. A function has to be continuous on this closed interval. So it won't work if the interval is open, and it won't work if our function isn't continuous. So let's look at a couple examples. So identify the location of the absolute maximum and absolute minimum value on the interval a to b. Does the function meet the conditions of the extreme value theorem? And here we have the graph of a function y equals f of x. And you can see, because I can draw this without picking up my pencil, it's continuous. We don't have any open holes, we don't have any discontinuities or jumps, and we don't have any sharp corners, so it must be continuous. And that means it meets the extreme value criteria of being continuous. Now, does it meet the closed interval? And the answer is yes. We've got a closed dot at A and a closed dot at B, so we're including it on the interval A to B. So that means that we can find the exact minimum value. Our function f is continuous on the closed interval A to B, so the extreme value theorem guarantees an absolute maximum, which occurs at x equals A. You can see that's the highest point on our graph, and an absolute minimum at x equals C. And this is the lowest point on our graph. Now, can we do this again for another graph? I want you to identify the location of the absolute maximum and absolute minimum values on the interval a to b. And then the question, does the function meet the conditions of the extreme value theorem? So let's think. Sorry, I mislabeled these. This should be a C in the middle and a B at the end. A has an open circle and C has an open circle. So we don't have a closed interval. Furthermore, we've got a jump discontinuity. So right here, f prime of x does not exist and our graph is not continuous, right? So we are neither continuous nor are we on a closed interval. So it does not meet the conditions of the extreme value theorem. So the function g is not continuous and it is only defined on the open interval a to b. So the extreme value theorem doesn't guarantee anything. We can't guarantee that we're going to have an absolute minimum or an absolute maximum. However, we still have an absolute maximum at x equals c. That's this point right here. Now, we introduce the idea of absolute maximums and absolute minimums kind of early, I think. I think we should be interested in local maxima and minima. So here I've got a graph, and in this graph, I go up and then I go down and then up a little bit more and then down a little bit more, and then I go up and end. Now my interval is closed because I'm including my two endpoints, and my graph is continuous. So the extreme value theorem would work for a graph like this. But you can see I have 2 points where I sort of bottom out before turning around and doing something else. So I've got a local minima here. I've got a local minima here. I've got a local maxima here, and I've got a local maxima here. And it's local because it just cares about the points around it. I'm only caring about the points near what's going on here. So I have 2 local maxima, 1 absolute maxima, and 1 absolute minima. So this leads us to the idea of critical points. An interior point C of the domain of F at which F prime evaluated at C equals 0, or F prime evaluated at C does not exist at all, is called a critical point at F. So here we can see I've got a graph, and I know that I've got something going on at the point C, but would I say that it's a maxima if it's not continuous there? No, I would not be able to say that, but it's still a critical point. So we say that critical points are candidates for local extreme values. So here in this graph, I've got the local value here, bottoms out at 0, but F prime of C equals 0, but you can see from the graph that it's neither a local minimum or a local maximum, and it's certainly not an absolute minimum or an absolute maximum. Instead, it's just a candidate. And if it's a candidate, that means we have to check to make sure it satisfies everything we want it to. So this leads us to the idea of how exactly do we locate extreme values on a closed interval. So we assume that we've got a function that's continuous on a closed interval. Remember, these 2 parts are very important. We can't guarantee anything using the extreme value theorem without these 2. So our first step is going to be to locate critical points in the open interval a to b. And this is what happens when f prime of c equals 0 or f prime of c doesn't exist at all. So you're going to calculate your derivative and set it equal to 0, and then solve to find out what value c is. Next, you're going to evaluate your function, your original function, at our critical points. Maybe we have 1, maybe we have many, and then evaluate them at the 2 endpoints, because those might be absolute minima or absolute maxima. The largest value we get is an absolute maximum, and the smallest value we get is an absolute minimum. So what does this look like? Here I've got a stone that is thrown vertically upwards, and the position function is s of t equals negative 16t squared plus 64t plus 80 on the closed interval 0 to 5. And I want to know, when does the stone reach its maximum height? So use the steps we set up just the slide before and see how far you can get. All right, welcome back. So we're interested in when the stone reaches its maximum height. So step 1 is locating the critical points by finding our first derivative where it equals 0. So we take our first derivative and we're left with negative 32t plus 64, and we're going to set it equal to 0 because we want to find out when we get values of t that will make our expression true. We solve for t and we end up getting the value 2. So we know that when t equals 2, we have some sort of critical point. We don't know anything about it because we don't have a graph, but we're going to find out in the next step. In this step, step 2, we're going to evaluate s of t at our endpoints and our critical points. So one endpoint is t equals 0, and when we plug that into our function, we get 0. Our next point is 2, that's our critical point, and we get 144. Finally, our last endpoint is t equals 5. So when we plug in 5, we also get 0. Step 3, our absolute maximum is 144 and occurs when t equals 2. So that's how we do it.